students, in last class we talked about the concepts of momentum and impulse and impulsive force, and I emphasized on the coefficient of restitution, which is known as the Newton's empirical formula, which states that the relative velocity between the colliding bodies along the line of collision changes just before and just after the collision. Just after the collision, the relative velocity along the line of impact is called velocity of separation, and just before the impact, the relative velocity between the colliding bodies along the line of impact is called velocity of approach. Separation velocity is always less than approach velocity. How much less? That is given by a fraction, a coefficient. What fraction of the velocity of approach is regained or restituted back? That fraction or coefficient is called coefficient of restitution. For instance, when you drop a body, it collides with the ground with a velocity of 10 meters per second. If the coefficient of restitution is 0.8, this means that 80% of the relative velocity between the ball and the ground will be regained. In other words, the body will bounce back with a velocity of 8 meters per second. And that concept was experimentally determined by Sir Isaac Newton. Therefore, that formula is called Newton's empirical formula, which states that velocity of approach into minus of E is equal to velocity of separation, or minus E into velocity of approach is equal to velocity of separation. This is one equation. It doesn't depend whether the collision is elastic or inelastic or perfectly elastic. We need to write that equation first. We have taken two bodies, they are moving along the same line. Just before the collision, let us assume that their velocities are u1 and u2 respectively. Their masses are m1 and m2 respectively. Just before the collision, this is the scenario, they are moving along the same line. And just after the collision, let us assume that they move along the same line with velocities v1 and v2 respectively. And we have assumed all velocities along positive x direction. Since the collision takes place along positive x direction and they move along x axis, therefore, this collision is called one dimensional collision. Either it is x direction, or it is y direction, or it is z direction, or along any direction, any line. When the collision takes place along a line and simultaneously the bodies move along that line, that collision is said to be head-on collision. Therefore, one dimensional collision can be called head-on collision. During collision, During collision, what will happen? The bodies will interact. This is the tangent. Without drawing the tangent, you cannot draw the normal. Once you draw the tangent, this is the normal, and these are the normal reaction forces. And this is the impulse of the impulsive normal reaction force. If it is plus, this will be minus. Due to this impulse, acting on M1 and M2, this impulse is equal to change in momentum of this body. This impulse is equal to change in momentum of this body, impulse momentum equation. If you write impulse momentum equation on the block 1, that's none other than the Newton's second law in integral form I told you in the last classes. Impulse momentum equation on this body states that the impulse, not impulse acting on the body, is equal to change in momentum of this body. Change in momentum is always final momentum minus initial momentum. This is the final momentum, and M1 is the initial momentum. So this is the change in momentum of the first object due to the action of this impulsive force. Similarly, the net impulse acting on the body 2, that is plus n dt, is equal to change in momentum of this body 2. The body 2 changes its momentum from m2 u2 to m2 v2. So change in momentum of the second body is equal to m2 v2 minus m1 v1. If you sum them up, this will get cancelled. You are getting m1 e1 plus m2 u2 is equal to m1 v1 plus m2 v2. Now this is called conservation of linear momentum constant. If you take this as a system, during the interaction, during collision, the net force acting on the system is 0. This is the system of particle. System of two particles. The net force acting on the system is 0. Therefore, the momentum of the system can be conserved. This is the idea derived from Newton's second law on the system of particles, which states that when the net impulse is 0 or neglected, the net momentum of the system remains conserved. Now we have two equations and two unknown quantities. First equation is conservation of linear momentum, equation number A. Or if you write in the form of scalars, all these vectors are pointing along positive x direction. Therefore, u1 you can write plus u1, u2 you can write plus u2, v1 you can write plus v1, v2 you can write plus V2. That's equation number A. In this way also you can write. Now Newton's empirical formula states that minus of velocity of approach into V is equal to velocity of separation. Approach velocity is the velocity relative to each other along the line of interaction. Interaction takes place along this line. This is the line of collision or line of impact. Along this line, what is the relative velocity of 1 with respect to 2 or 2 with respect to 1? U1 minus U2 or U2 minus U1. Velocity of approach is U1 vector minus U2 vector. Similarly, separation velocity is the relative velocity between these two bodies along the line of collision, that is V1 minus V2. If you write here U1 minus U2, you should write here V1 minus V2. If you change the order U2 minus U1, you have to write V2 minus V1. And without any vector sign if you want to write, because all the vectors are pointing along positive x direction, therefore you can write all these vectors as scalar. U1 is plus U1, U2 is plus U2, V1 is plus V1, V2 is plus V2. In this way also you can write. Newton's empirical formula is the concept. Conservation of linear momentum is the concept. So, solution of one-dimensional collision problems are based upon two concepts: conservation of linear momentum and Newton's empirical formula. We have how many unknown quantities? These two unknown quantities are the velocities of the colliding bodies just after the collision. We need to calculate these two. U1 and U2 are the velocities of the colliding bodies just before the collision. These two are to be calculated. So, we have two unknown quantities, V1 and V2, and we have two equations, and just we have to solve these two equations. I will tell you how to solve. Let us redraw the diagrams. Just before the collision, and this is the scenario just after the collision. Just before, just after the collision, just before the collision. We have developed two equations. One is conservation of linear momentum, which is given as m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is the initial momentum and this is the final momentum. Equation number 1. Next, the Newton's empirical formula states that minus A is the coefficient of restitution into U1 minus U2 is equal to V1 minus V2. Regrouping these equations, we have to solve for V1 and V2. Multiply the equation 2 with same 2, both sides. minus m2 v2 plus m2 v2 will get cancelled. So you are getting equation 1 plus m2 times the equation 2 gives us, you take the left hand side, you take u1 common, so you are getting m1 minus em2 into u1 plus m2 u2 plus minus into minus plus m2 e into u2. m2 u2 take common. If you take m1 u1 common here, you are getting 1 plus, you are taking u1 common, then you are getting m1 minus e into m2. Then you take u2 common. You are getting m2 plus e into m2. This is equal to m2 v2 minus m2 v2 will get cancelled. You are getting m1 v1 plus m2 into v1. You take v1 common, you are getting m1 plus m2. In the next step, you are getting v1, the final velocity, or the velocity of this first body just after the collision, that is v1 is equal to m1 minus e m2 by m1 plus m2 into u1 plus m2 u2 into 1 plus a by m1 plus m2. Similarly, if you add equation 1 with minus of the equation 2 into m1, you will be able to cancel u1 factor to get v2. We are getting m1 u1 plus m2 u2 plus m2, it is m1 into a u1 minus u2 is equal to m1 v1 plus m2 v2 minus m1 into v1 minus v2. Equation 1, this is equation 1. Minus second equation, this is second equation, into m1 minus of m1 into this will be equal to plus m1 e into u1 minus u2 and m1 v1 minus v2 is subtracted from equation number 1. Well, so which is getting cancelled? This factor will get cancelled. As a result, you are getting in right hand side m1 plus M2 into V2. And left hand side you are getting, when you group it, U1 into M1 plus M1E, or we can just write by taking M1 out of the bracket, 1 plus E plus M2U2 minus M1E into U2. So, just you can take common U2. But in the bracket, that this will be M2 minus E into M1. The next step, you are getting V2 is equal to M1 into 1 plus E by M1 plus M2 into U1 plus M2 minus EM1 by M1 plus M2 into U2. You have to remember this two as two formulae of any final velocities of the body 1 and body 2 just after the collision. So, I will tell you how to use these two equations in solving one dimensional problems of collision. So, we have prepared these two formulae and we can discuss few cases. For instance, body M2 is at rest and body M1 strikes the body 2 while moving along positive x direction. In this case, you can write U1 equal to V0 and U2 is equal to 0. Substituting these two in these two formulae, you are getting V1 equal to M1 minus A into M2 by M1 plus M2 into V0. Since U2 is 0, because the second body is stationary, so this factor will vanish. So, this is the velocity of the body M1 just after the collision. Similarly, the velocity of the second body just after the impact or collision can be calculated by using or putting U1 equal to V0 and U2 equal to 0. The second term will go. Eventually, you are getting V2 equal to M1 1 plus E multiplied with M1 by M1 plus M2 into V0. If one body is stationary, you can write these two expressions of the final velocities. Case 2. If two bodies are equally massive, masses of two bodies are same, then what will happen? You can just put M1 is equal to M2, let it be M let. Then U1 can be written as 1 minus E by 2 into U1 plus u2 into 1 plus e by 2. And v2 is equal to 1 plus e by 2 into u1 plus 1 minus e by 2 into u2. So, these are the expressions for v1 and v2 when this condition is satisfied. Let us put another condition. If E is equal to 1, that is the condition for elastic collision. Collision is perfectly elastic. Then putting A is equal to 1 in both the expressions, the master expressions or master equations, we are getting V1 is equal to M1 minus M2 by M1 plus M2 into U1 plus 2M2 by M1 plus M2 into U2, and V2 is equal to 2M1 by M1 plus M2 into U1 plus M2 minus M1 by M1 plus M2 into U2. You can remember this too as the formula for the final velocities of the objects for completely elastic collision. Under these conditions, we can write another subcondition. If the collision is perfectly elastic, and M1 equal to M2, then if you use this formula, put M1 equal to M2, already have put E equal to 1 in the master expression. To get V1 equal to, this factor will go. V1 is equal to U2 and V2 is equal to, this factor will go. V2 will be equal to E1. V1 equal to U2 and V2 is equal to U1. So, we can write the bodies just exchange their momenta and kinetic energy in perfectly elastic collision when the masses are same. So, these are some sort of concepts we can derive from the master expression. However, when you solve the problems from the basics also, you can write the Newton's empirical formula and the momentum conservation equation, and you can solve. It may take couple of more times, couple of more minutes, but you will get your answer with least pressure on your minds. Let us take an example. Two bodies of masses 1 kg and 2 kg moving with velocities 2 meters per second, that is u1, and u2 1 meter per second. We need to calculate v1 and V2 if the coefficient of restitution is 0.5, say. This is the question. Either you can directly apply the formula or you can start from the scratch. Both the methods are self-sufficient, but always few problems you should try from the scratch. Write Newton's empirical formula and conservation of linear momentum. Newton's empirical formula states that minus of, first to write the formula, minus A into U1 minus U2 is equal to V1 minus V2. A is equal to 0.5, U1 is 2, U1 minus U2, these are all positive direction. So, you can write U1 equal to plus 2, U2 equal to plus 1 is equal to V1 minus V2. So, V1 minus V2 is equal to minus 0.5 into 2, that is 1 into minus 1, or you can just write 2 minus 1, that is 1 into 0.5, that is minus 0.5. Next, conserve the momentum of the system just before the collision and just after the collision. Its mass is 1 kg, its mass is 2 kg. Initial momentum is equal to final momentum. The final momentum is given as m1 v1 plus m2 v2 is equal to initial momentum m1 u1 plus m2 u2. m1 is 1, v1 is v1, m2 is 2, v2 is v2, m1 is 1, u1 is plus 2, m2 is 2, u2 is plus 1. So, you are getting 1 into 2, that is 2, plus 2 into 1, that is 2, 2 plus 2, 4. So, v1 plus 2v2 equal to 4. Simple technique. We are getting two equations, just you have to solve. Write the equation number 1 and solve them. Multiply with 2. It's getting cancelled. So, 3v1 is equal to 4 minus 0.5 into 2, that is 1. That is 3. So, v1 equal to 1. Answer. And substituting v1 either in this equation or in this equation, you can get v2. If v1 is equal to 1, v2 will be equal to how much? 1 plus 0.5, that is equal to 1.5 meter per second. So, the bodies will move with velocities 1 meter per second in positive x direction and 1.5 meter per second in positive x direction. Well, sometimes they gave the velocities, initial velocities in negative x direction. In this problem, let us take the same problem of masses 1 kg and 2 kg. This is moving in positive x direction with 2 meter per second, and this is moving in negative x direction with 1 meter per second, just twisting. What are their final velocities just after the collision? Let us assume that they are moving in positive x direction with velocities v1 and v2 respectively. We can change the concepts, Newton's empirical formula, and the second concept, the conservation of linear momentum, both the concepts can be used. If we use this, just you have to change. This remains as it is. E1 is plus 2. U2 is moving in negative x direction. Therefore, this will be minus 1 is equal to v1 minus v2. We have assumed this velocity is in positive x direction. So, just simplify them. Plus 2 minus 1 plus 1. So, 3 plus 1, 2 plus 1, that is 3 into 0.5, that is minus 1.5. Next, apply the conservation of linear momentum. M1 is 1, V1 is plus V1, M2 is 2, V2 is plus V2, M1 is 1 and E1 is plus 2, M2 is 2. Here there is a change. Instead of plus 1, you should write minus 1 because the second object is moving towards negative x direction, minus 1. So, you are getting V1 plus 2V2 is equal to plus 3 minus 2, that is plus 1. Plus 2 minus 2, it is not plus 1, it will be 0. Now, you solve these two equations. V1 minus V2 is equal to minus 1.5. If you multiply both sides with 2, getting cancelled, 3V1 is equal to minus 3. Therefore, V1 we can just write minus 1 meter per second and V2 is equal to V1 plus 1.5, V1 is equal to minus 1 plus 1.5, that is 0.5 meter per second. So, this will move with velocities. Since you are getting negative, you have taken positive x direction is positive, but you are getting negative answer. Therefore, this object 1 will physically, it will move back in the sense negative x direction with a speed of 1 meter per second, and the second object is moving with a velocity of 0.5 meter per second in positive x direction because we are getting positive result. This is the physical analysis of the situation. In this case, we are getting both positive. This means this moves with 1 meter per second and second body moves with 1.5 meter per second along positive x direction. So, if you are given with negative velocities, so you have to alter the direction or put the negative value of these vector quantities. In physics, when you start doing the problems, instead of scalar, you write them as vectors. When you will get some ideas, get some mastery, without writing the vector sign also, you can do the problems considering all these quantities as vectors. So, these are two fundamental examples to just doing the problems of one dimensional collision by using these two concepts without directly using the formulae. Now, I will tell you the expressions which will give us how much energy is wasted during collision if the collision is not perfectly elastic.